Okay, I'm Sam Bourgault. I'm a PhD candidate in the Media Arts and Technology program at the University of California, Santa Barbara, and I work in the Expressive Computation Lab. That's Jennifer Jacobs' lab, if you know of her work. Today, I'm going to present you the digital fabrication system for craft that I've developed as part of my dissertation work and the broader implication of using craft as a framework for digital fabrication systems. So in the context of my dissertation, I refer to craft as an iterative process of working with materials. And while using this very broad definition, which encompasses like many specific practices with their own set of requirements, most craft have in common the goal to produce high-quality artifacts through in-depth and skillful engagement with materials. So using this definition, craft also encompasses digital fabrication. I'm sure you're all familiar with it, but the practice of using computer-controlled machines to fabricate artifacts. Like other craft, digital fabrication focuses on working with the opportunities and the limitation imposed by the inherent properties of materials. And while this is not represented on the slide, digital fabrication also involved manual dexterity, such as in tasks like leveling the workspace, preparing a part or a surface for fabrication, and cleaning up the fabricated artifacts through sanding or cutting unwanted sections. Yes. Like other craft, digital fabrication also involves risk and failures that a craftsperson can navigate by understanding the interaction between design features, machine operations, and material properties, such as in the work of the artist LIA that I really like, who uses thermoplastic to create these butterfly-like effects that harnessing the filament aspect of thermoplastic printing. Digital fabrication emerged from a place of craftsmanship, but it evolved as an outcome of the manufacturing industrial pipeline, which negated in part its relationship to making things by hand. So as digital fabrication machines have grown in use, much of the research and engineering has focused on automation, repeatability, and simulation, including highly processed materials, entirely automated processes, and material agnostic toolpath generation, using slicers, for instance. Moreover, the available workflows in digital fabrication make little space for manual interventions and conceal material and machine knowledge into computational abstractions by promoting form over process through often a linear design and fabrication progression. This is what researcher Anna Twigg-Smith from University of Washington call the canonical digital fabrication workflow that goes from CAD, CAM to CNC in a linear fashion. Therefore, the main objective of my research is for digital fabrication workflows to align more closely with principles found in traditional craft, which tend to make explicit this relationship between material, tools, and the human in the making process. And I think that's important because working at the level of material and machine behaviors is necessary to for the viability of digitally fabricated artifacts. Broadening digital fabrication practices can also lead to innovation, and promoting values of customization associated generally with craft can support the development of unique, meaningful, long-lasting products which moves away from a market of disposability. So in the work that I will present shortly, I try to answer the following research question, and try is really the key word here. So first research question that is guiding my work is how can a closer engagement with machines support new design spaces? How can digital fabrication system make material properties discoverable rather than hidden in computational abstractions? And how can fabrication workflows integrate manual and computational processes? to explore these research questions, the methodology I engaged in so far is the development of digital fabrication system in collaboration with craft professionals, specifically ceramicists, the production of artifacts through research through design and autobiographical methods, and the application of materialist and craft theory to system development. So in this presentation, I'll walk you through 3 digital fabrication systems I developed as part of my PhD work, which include a programming system for clay 3D printing, an interactive workflow for ceramic decoration, and a parametric system for CNC milling surface textures. So, okay. So artists have been at the forefront of the exploration of alternative approaches to digital fabrication for craft applications. So for example, Oliver Krieg, LIA that I mentioned earlier, and Sarah Rosalena are designing artifacts in wood, plastic, ceramics by specifying custom machine toolpaths, which allows them to achieve unique aesthetic qualities that leverage the material expressivity that they employ. Researchers have also developed new digital fabrication technique that harness material properties. These alternatives have shown that granular control over machine toolpath, often using CAM-based tools for design tasks instead of CAD-based ones, enable the creation of a material structure that would be unachievable by other means, really. So CAM-based design for additive fabrication, however, has primarily focused on thermoplastic printing. So with this first project, I aim to extend these approaches to clay 3D printing. Clay 3D printers, if you're not familiar, enable the fabrication of 3D structure by extruding small coils of clay and then layering and compacting them in succession. While using completely different design strategy, clay 3D printers draw from the practice of hand coiling, which consists of building vessel, again, layer by layer, using hand-rolled coils of clay. And ceramicists that use coiling technique can build vessels that show a wide range of aesthetic and functional qualities. Inspired by my collaboration with expert ceramicist Pilar Wiley and how she traces a path with her hands in space when she creates her vessels, I wish to develop a system that could parameterize a machine toolpath in a similar way. So, and to encapsulate this idea, I introduced the notion of action-oriented workflow, which is also in the title of this presentation, a term that I define encompasses both manual and computational modes of fabrication. So in action-oriented workflows, form results from each action taking place between the craftsperson, the machine, and the material, such as the way Pilar calls her butt, executing systematically a little rotating motion as she coils with her finger, which is really beautiful to watch. And I'm using a new materialist framework here to define the term action as the result of multiple agencies that come together rather than an illomorphic perspective where the human just imposes their will onto matter. Okay, so with this in mind, I developed Colloquium, an action-oriented, domain-specific visual programming system that enables craft people to specify machine toolpaths mathematically. Colloquium is designed as a plugin for the popular software Rhino, implemented using custom Python scripts, component in Grasshopper, as you can see here. Colloquium was created in the context of an artist residency, very much inspired by Laura's work of experimental textile residency. This one happened in my lab during the summer of 2022, and I had the chance to collaborate with 2 professional ceramicists, Pilar Wiley and Ivy Farber. And then the little icons that are shown here, I'll use them from now on in the presentation instead of using the Grasshopper modules, and clarify a little bit the visuals this way. So the insights of the ceramicist into manual ceramic inform Colloquium's computational features. Programming in Colloquium is centered around the toolpath unit generator, which exhibit 4 modifiable parameters, including the radial form of a layer, the scale of the layer, with the layers with respect to one another, their translation, and the rotation. And the shaping parameter can be modified with function operators and Boolean operators that all worked at the level of the toolpath. So by combining different operators together in different way, a craftsperson can generate a wide variety of complex toolpaths. This example shows that using the same combination of function operators, but on different shaping parameters can result in very different form. Here, a combination, multiplication between a sine and a linear function create this sinusoidal gradient that can be applied, for instance, on the scale, changing the profile of the pot, or on the radius, changing the radial shape of the object. So our evaluation of the system revealed critical consideration of action-oriented system for clay, rapid and iterative variation enabled by the parametric system mirror some of the aspects of how craft people work with material through continuous feedback. And then mapping continuous and discrete mathematical function onto formal component of a vessel provide opportunities to harness material properties for creating expressive forms and surface textures. And finally, low-level machine actions representation supported by Colloquium enable the planning of human-machine material collaboration, as shown in the creation of the handle for this teapot, where the craftsperson, aka me, in this case, use the tools and fingers to shape the handle as it was printing. So these findings indicate that action-oriented workflows present exciting possibilities for digital fabrication system research, and it will, as you will see, it informed my work, the next projects. I use Colloquium as part of my art practice as well. Recently created this kinetic installation in collaboration with my friend Emma Forg, that was trying to abstract the human body in soft and hard material that interact kinetically together. And then, yeah, this was presented at IZEA 2023 last summer. So with Colloquium, I began exploring the domain of ceramic decoration as well, and discovering that this space, a space where manual and it's a space where manual and computational methods can enhance each other to create interesting artifacts. Which led to the next project I want to present today, done in collaboration with my colleagues, Mark Toka, who's also a student in Jennifer's lab, ceramic artist Camilla Friedman-Gerlich, who's now, I think, a postdoc in Leah's Bickley's lab in New Mexico, and Professor Jennifer Jacobs. Ceramic ornamentation is concerned with decorating clay vessel using various techniques encompassing both additive and subtractive methods. And these techniques generally involve the creation of ornamentation through two different strategies, either the positioning of each element individually, which is very flexible. You can decide where you put each element, but it's usually laborious to accomplish systematically, or the use of global templates. In this case, that's an underglaze transfer sheet that can cover a lot of surface quickly, but does not conform to very complex vessel geometry. But while each technique has its unique set of requirements, they all share the need to adapt to the ever-changing nature of a material like clay. The transformation process of wet clay into solid ceramic involve different drying and firing stages, during which the clay undergoes shrinkage and often distortion in very unexpected ways. So to support the dynamic qualities of clay and the different spatial organization levels of decorative elements on pottery, we developed Ceram Wrap, an adaptable workflow that enables the fabrication of parametric pattern templates that conform to radially symmetrical vessels, and then on which different ornamentation technique can be applied through. Ceram Wrap computational tool includes the parametric creation of patterns where a decorative element is drawn in Rhino and projected onto the surface of a digital model, and then modified in number, scale, rotation, and translation using transform functions. And then the second computational tool is a selective unrolling function to generate a two-dimensional pattern template here illustrated by the green curves. And so a craft person that engaged in the full Ceram Wrap workflow first creates a physical vessel. In this specific example, they throw a ball on a wheel. Once the piece is made, it needs to dry to its ideal drying stage, depending of the decoration technique that is being used. Here, the craft person waits for the clay to be leather hard. And then taking measurement on the physical vessel, the craft person creates a digital model using simple Rhino functionalities and generates decorative elements using, as I said, Rhino drawing tool. A pattern is then created with Ceram Wrap's pattern generation tool. The pattern is unrolled and then fabricated here on a laser cutter, but it could be on a vinyl cutter or other 2D type of fabrication. The template is installed on the vessel, but if the template doesn't fit perfectly due to distortion or imperfection, the craft person can adjust the model and regenerate the pattern until a desirable fit is achieved. The fitted pattern is installed and the decoration applied through. In this example, we drilled holes in the bowl to create a colander, and then the piece can follow the traditional ceramic pipeline, which involve waiting for the vessel to be bone dry, going through bisque and glaze firing in the kiln until we get the final piece. We applied this workflow to a set of examples that covers 3 fabrication techniques, slab making, wheel throwing, and 3D printing, and 4 decoration techniques. So making this example artifact with Ceram Wrap revealed critical aspect of manual computational approaches to ceramic surface decoration. First, manual computational workflow can support different levels of tolerance in ornamentation alignments and can be used by craft people that show various degrees of skill. Low degree of skill, me and Mart, and high degree of skill, Camila, who's just an expert ceramicist here. Then digital fabrication procedures and existing manual craft technique can be integrated into the same workflow. Here you see Camila making this beautiful Klein bottle with the body decorated with a diamond-shaped motif generated with Ceram Wrap. And finally, enabling rapid changes in the design of pattern templates accommodated for the shrinkage and distortion of ceramic vessel. So this demonstrates a little bit the opportunities of digital fabrication system in supporting a form of nonlinear manual workflow. It's written breathe, water, so I'll take a tiny break. Okay. So while developing Ceram Wrap and Colloquium, I started being very interested in the theories of materiality that are often used as a framework for thinking about designing with non-human entities. So in this case, machine, materials. And in these different accounts, philosophers and researchers theorize the complex relationship that takes place between human, machine, materials. Material theorists have written about non-human agencies, and craft theorists have discussed specifically the role of materials in the fabrication process. In HCI, this entanglement has served as an analytical tool to understand material practices, for instance, and or as a starting point to design speculation. And what these theories have in common is they challenge the human tendency for anthropocentrism, which impacts the way we interact and make things, despite the reality where material and environment have like significant roles in the fabrication process. So with this next project, I wish to study the impact of using materialist theories in the making of a digital fabrication system, which led me to a fourth research question for my PhD. How can system development informed by materialist and craft theory support novel modes of production between humans, materials, and machines? Being inherently abstract, though, theory can be difficult to implement concretely in a system. It often lacks clear application guidelines. So to remediate to this issue, researchers Dalsgaard and Dindler proposed the use of bridging concepts, an intermediate level knowledge that helps connect theory and practice. This is how they represent it in their paper, where they developed this idea. And so making is a time-based rhythm of action, said craft theorist Richard Sennett, a statement that I think transcends most of materialist theories regarding fabrication. So because of its importance theoretically and practically, I decided to focus on action as a bridging concept for this work, which in the literature refers to the site of convergence happening when tools and material touches during the making process. So surface texture production in woodworking is a good example, I think, to think about action. As exemplified in this video by the artist from a seed, the practice typically involves a craftsperson executing a sequence of carving actions systematically using various tools and techniques, in this case, making little spherical holes using a Dremel, for instance. In contrast, CNC milling machine tend to follow the more traditional CAD/CAM workflow that I presented earlier in the presentation, where the artifact geometry defines the machine toolpath rather than the other way around. Oops, I forgot to click. Tick, tick. Automating, which automates and therefore obscures some aspect of the carving process. So in this next and final project that I want to share with you today, I wish to enable a more craft-like experience when using a tool like a CNC machine by mirroring some aspect of manual carving actions. So this project is therefore a case study in developing a system that is, in this case, a computational tool for making surface texture with a CNC milling machine that consciously pull from abstract knowledge, in this case, materialist and craft theory, and using action as the bridging concept between both. And this work is also informed by my two previous projects, especially the notion of action-oriented system from Colloquium and pattern creation in CeramWrap, as developed in CeramWrap. Subtractive surface decoration in woodworking appears in the customization of furniture, the creation of textured wall panels, or the making of intricate sculptures. And so looking at a selected design space and analyzing the way surface textures are organized in space, I identified a set of formal properties, including the grid, the movement of the tool, and the boundary within which the tool action happens. And these I identified as the components of the carving action. So with this design space and analysis in mind, I developed a system called Millipath, which focuses on design and fabrication of carved patterns using a CNC milling machine. Millipath is designed as a programming-based web application that implements carving action with functions for grids, movements, and boundaries. Each grid repeats a specified movement within a designated boundary. That's kind of the design idea behind it. And then the rotation, scale, visibility of each movement can be mapped to properties of the grid. So in this case, I'm changing, in the programming interface, I'm changing the rotation values at each point of the grid, setting it to random here, which randomize the orientation of the movement. In this case, the movement is these 4 parallel linear movement with a parabolic depth function that will be produced across that grid with now random rotations. So once the design is done, the craftsperson can download the code file and run it on a shop.cnc machine. Here you see an example of custom boundaries on the top left where the circle has been cut, and then overlaying grids on top of each other to create more complex patterns. So Millipath offers some benefits over traditional CAD/CAM workflow typically used in CNC with CNC milling machine. It enables craft people to leverage machine properties as design features. So for instance, the CAD model of a glass designed by a Design Path Studio is perfectly smooth, but by increasing the step over of the end mill, the designer were able to create linear texture on the mold. Note that that was not done with my system. That's just an example out there. So while this is an unconventional CAM operation, it opens up new ways of doing subtractive fabrication, and Millipath offers a formal representation to achieve that kind of stuff. Not this example, but I want to clarify. And it also enables craft people to specify machine toolpath through parametrization, as opposed to having toolpath being subservient to the geometry of the fabricated artifact, which I think are interesting here. A big part of that project was involved documenting my research to design process systematically, as systematically as I could. I produced three types of artifacts, including a stool and wooden inlaid tray that I have here. Those are all prototypes, so like you can judge my craftsmanship. And some cups. So awesome. Yeah, sure. Yeah, that's not been sanded, and it hasn't been varnished or anything. So just there's more work to happen there. So here's just a little images of the creation of this tray. The previous one was the creation of the cups. Yeah. So using Millipath to make, you can also pass the cups if you want. I forgot to say, these guys were done with Colloquium, the first tool I presented. They were the thing that could fit in my package, but if you want to pass it around, you can as well. There's a little bit of soil in that one because it used to host a plant, but the plant died, unfortunately. So yeah, we're not very good at maintaining plants in the lab. So using Millipath to make these artifacts showed that fine control over machine actions support fine aesthetic details, and small changes on machine action make big changes in aesthetic quality. So for instance, using the same toolpath, but changing the end mill that is being used to create the carving pattern result in very different outcomes. And then the way material behave in response to the machine action support the development of material knowledge for the craftsperson engaged in that process, and create some sort of hierarchy of use among these materials. So, for example, very uniform material like foam and MDF, so like foam and MDF were ideal as prototyping material because I could only test the different machine parameters, knowing that wherever the machine carves, it would result in very homogeneous outcomes. Plywood, on the other end, requires more careful planning of the machine action. It delaminates easily, and then it cuts better in the direction of the wood fibers, as shown here you see that the horizontal lines are pretty clean, but then the vertical line have a lot of like notches and but then some of the work that I've been exploring with this tool also showed up sometimes some of the material opportunities of plywood emerge when starting to reveal the multi-layer quality of the material, which became an aesthetic feature in further artifacts, specifically this tool, which I'll show quickly after. Finally, millipath modularity enables a craft person to work at different levels of design abstraction. Here, the local scale, which is the carving action, the global scale, which correspond to the grid, and then what I call the collective scale, which correspond to layering grids together. And is there something else I want to say about this? Oh, well, an example of that is for this tool, which I'll show in a sec. Part of it, at least, I created the final texture was the combination of a dense grid with shallow circular carving actions and followed by a looser grid made of deeper circular carving action, which revealed the multi-layer quality of the plywood I was using. So here's all of the artifact collected in one image. You kind of see this tool underneath, and yeah, the other objects that are on the table. So I wish to conclude with, that's my last slide, with some final observation that came out of this research to design process with respect to my initial ideas of post-human engagement. So first, decentering the human and dismantling hierarchy during the fabrication project was very challenging and if not like impossible to achieve completely, I think, within a human-defined context. However, more authentic interaction with machine and material arose from repeating fabrication actions, which resulted in the systematic development of my own machining and woodworking skills. And this leads me to argue that developing fabrication expertise is an intrinsically post-human practice because of the time and the dedication it requires to understand and predict material behaviors dynamically. So I hope that in the future of post-human HCI research, more focus will be given to the skillful craft work as a way to deeply listen and connect with the material world that is around us. Thank you. That's the end of my presentation. Thanks for being here. And if you have any questions, I'll try to answer. Thank you.
I've got questions.
Sure.
Kind of like maybe a simple one, but in the Colloquium, you had like a sign modifier, but there's lots of different types of modifiers. Some use it like oscillators, which has different shapes, should we say?
Yes.
Is that a part of the system? Maybe you mentioned that. Plus,
so let me just go back to kind of the object definition. So far I've implemented a subset of like functions, but I found that even that subset is very like it's by combining them, by adding or multiplying signs together, you can like classic Fourier transform stuff, but like you can get so much variation. And then I found that like using a continuous like function, so like linear sine, exponential to a certain degree function are really good for shaping I don't know, like a macroscopic level detail in the toolpath, but then using more discrete like function like a step or square wave are great for texturing. And with this combination of these five, I've been able to do a lot of different type of things, but I'm sure maybe you have ideas. There must be other things that could be. Oh yeah, I think that light was there for 2 seconds. So
did you consider putting these icons into the GUI, like so people can see, like obviously they can see how it's going to come out as a totality, but like looking like through the steps of each node?
Oh, like representing the way for you.
Yeah, like all of the nodes as they come.
I haven't thought of that, but that would be a really cool. I think it would be really cool, mostly because we've been working with ceramicists in our lab, and mathematics can be a tool for them, but not necessarily. And so we had some response to that tool that was like, oh, I need to understand the greater impact of like, what does that mean to apply a sine wave? Like, well, on the profile, well, it means you're going to start getting curves on the profile. So maybe having some sort of representation before it's being plugged in the toolpath unit generator might be actually a good way to like transmit some of that information. Thanks for the comment.
I'm curious, I think it's like kind of like the ceramicists would feel, but how do they feel about this workflow? I think you can do it. Like while you can modify the things in Manual-Computational, you are taking all of it. Like they're not interacting with material, right? Yeah, I mean you have an example of like the printer is printing a coupon and you're making a handle, but so maybe you address it there, but I think like otherwise like, you mostly are not interacting with query. So like how do they feel about that? Or is this tool made for people like non-native? Maybe they're asking for a different set of.
Yeah, that's a very good question. I think, well, there's different answers. I think one of them is the tool was developed during the residency. So I was on the computer with them, and we would like talk about the type of visual effect that they wanted to achieve. And it's not shown in this presentation, but there's a lot of the work was done, like we're both looking at the computer, we collaborate together. And I think from that standpoint, I mean, they were pretty excited about it. And just as a comment, the ceramicists that participated in the residency, they submitted application because they were excited about the possibilities of 3D printed. So that printing, so which might be biased a little bit for like it doesn't necessarily encompass all ceramicist opinions, but Avi and Pilar at least were excited of like working in collaboration with a tool like that. The other thing I think, or the other aspects, other answers for this question is that what we realized in our lab is because we had a second residency last summer, so 2 more people came in and started working with those kind of tools and other tools, not just Colloquium. They were using 3D printed as a tool within a greater workflow. So for instance, Anha Pike was systematically printing parts of her objects and then assembling manually these parts to create like bigger shape and bigger figures, and which I think like shows the, I don't know, like the creativity of people, of artists using tools like this, where they still liked, and like they all shared the fact that like it's enjoyable to touch the material, and the goal of these tools or my tools are not to remove that at all, but then they might be just a component in a bigger artistic workflow, which ended up being the case for some of our residents, so maybe I hope that answers your question. Hey.
Thanks for the presentation.
Yeah.
So I was curious if you can reflect with us just around like the difference between like Manual-Computational, which it sounds like it was focusing more on like your practice working with the tool in comparison with the other two projects where you had artist collaborators. Like how did that feel and how did that like impact your like research process?
Yeah, good question. Well, first of all, working with experts that know intrinsically in a very embodied way the material they work with is like, it's so amazing. Like for the clay project, it felt like we were as a group all learning from each other. And I think for both like more like the computer scientist researcher and the ceramicist, it brought our understanding of computation for them and clay for us, like the learning of the requirement of working with clay were done very quickly or more quickly. And then working with wood, where I was alone with a CNC machine for the most of like the last year, it felt like I had to come up with a strategy for learning. Like I have done subtractive fabrication before, but not in this way. And where with a collaboration with professional was like very quick and okay, I have a question. I don't have to Google it. I can ask them and they have like a wonderful answer to give me and strategies to try. And then when working alone, that was not the case. So a lot of that research to design work was trying to like work little bits by little bits and then slowly build up on, okay, now I understand how plywood kind of behave when I apply this type of movement with that shape of CNC and mill. So I guess that's like one of the main difference. I wished I had expert woodworkers with me. I think that would have been like very helpful. And I mean, it could still happen. I guess that's a first version of this project, but yeah, I guess I would say that's the main difference. And I had the methodology changed a lot in trying to understand the material. Does that answer your question?
It does. It just makes me have more questions.
Oh, yeah.
I guess because I imagine the tools that you're designing in a Rhino environment when you're working with another artist, you're like, oh, what would be helpful to you? And like, I'm going to like the UI is like it's a collaborative thing because you're trying to make something that you can make, but that also is helpful to someone else. I'm curious then, like when you were designing Manual-Computational, you're designing with your aesthetics or like your needs in mind.
Yes.
And like how that might look different if you were designing with a collaborator. Just, I don't know, just thinking about like the process. I mean, it's just for you versus when others.
One's node-based and the other one's like.
Yeah.
Correct.
Yeah.
Yeah.
It's JavaScript, but then it's like, oh, well, yeah.
Yeah, that's why I mean, at this level of the Millipad project, like the interface was not a consideration. I was like, I know syntactic programming is not the easiest for the end user. So that's why the work focused a little bit more on the trying to understand how theory around material can be reinterpreted into a system rather than like supporting a specific group of people, I'd say. But then, yeah, you're right. Like when I was developing Colloquium, like they would say, oh, I wish I could like, instead of using these maths, could there be like some direct manipulation tools for some of it? And I was like, oh, sure. Like Pilar especially was like, oh, I wish I could just use a curve to create a profile, but then use the maths to create a texture. That's something I implemented with her and that we worked on together for a few weeks, for instance. So yeah, that was and the outcomes are different. And that's why I'm going to OSAC. It's like I wish Colloquium be even more usable for people. And like, I think talking to the open source community might be a good way to understand a little bit more, like, oh, well, how do you share that type of knowledge and information and document and that kind of stuff. Mealypath is not at that stage yet, I would say, because it was like, I'm a programmer, I feel comfortable with that, but this, I would not say that that's a tool for woodworkers. I would say that's just a tool to try starting understanding how we, like, the expressive ways of working with CNC machine that could align with some woodworking practices, but yeah.
Is the idea with Manual that you can work with it like iteratively, so you do a small bit, you see the result, and then because you're talking about collaborative scale, like overlaying things. So it's like, I do a bit on whatever material I have, and then based on what I've done, I'm now maybe slightly modifying what I need to do for the next section, but then I'm doing something that exists over the top, right?
Yes, totally. Actually, what I one of the, so this paper is in review. Hopefully it will come out at one day, but that's in the hand of the reviewers. Is that both the modularity of the functionalities, which here are defined as grid movements, which are the main and boundaries, but grid movements are kind of the main object that represent the textures. But also the modularity of the machine became a place for incorporating design decision, both at the computational level and at the machine level. I don't know if you've worked with the ShopBot CNC, but there's a lot of little functionalities that enables you to stop the cut and then midway change the hand mill bit, zero the Z, move your XY0 to another place. And so, like, the combination of both the modularity of the code that can be stacked and done iteratively, like you mentioned, where like, okay, you do a first layer and like, okay, I have this little code object that exists that could be just like overlaid. And some of the way that machine that I haven't programmed, but that are incorporated in that machine became very, or gave a lot of flexibility to design and fabricate at these different levels, I guess. So, yeah, that's one of the things that that's the takeaway I try to express in this work. But thanks, yeah, for the question.
Did you ever consider trying to like capture gestures or like body actions that would be like a part of the input to the system?
That's my next project. That I'm not presenting because it's very at its early stages, but I started working with a robotic arm, like a cobots, where you can teach the robot to manually to do certain things. So I'm trying to develop different type of robotic interaction models that are both maybe using some part of pre-programmed toolpath, but are also taking into account, I'm not sure how this will evolve, like either some sort of computer vision that might be physical instead of like vision, or using the like teaching feature of those cobots as a way to generate toolpaths and so yeah, that's kind of the next next step that I'm trying to look at as a input within those like with these type of computational systems. Yeah, cool. Thanks. Oh, there's a chat. Oh, Sandra is asking, why do you not 3D scan then? That was maybe earlier. Well, so we're actually, I don't know if that's supposed to be secret, but we're actually working on a specific scanner in the lab right now. And that will that kind of enables where the outcome of the scanner will output a toolpath that is directly usable by fabrication machines. So it's in the process. I'm not sure. Sorry, Sandra, I just saw your question. I'm not sure if that related to something I said earlier, but one of the things with 3D scan that at least I experience is it gives you this kind of artifact that is messy point clouds that you then have to like clean up and yeah, that's something I haven't necessarily looked at because of the hurdles and obstacles that come from the 3D scanning process, which I don't think we have figured a really good way to do yet, though I'm not an expert in 3D scanning, so maybe there's I'm sure there's some technology I'm not aware of, but the LiDAR and structured light type of scanning methods doesn't necessarily or need additional work to then be even processed by a 3D printer, for instance. Sorry for the context was posed earlier when you were presenting the second project. Oh yeah. So for Ceram Wrap, yeah, we decided to go with the a simpler version of using just the simple loft functions and rotational function to create. Sorry, so I think that was here. Though like the reviewers did ask why we didn't consider scanning, so I totally get it, but we like creating a bowl shape with a lofting or a rotational operation in Rhino, like there's some learning or there's some skills in CAD to have for sure, but it takes literally like 2 minutes. And we considered that like 3D scan would actually take us probably like half a day to like do the scan effectively and then clean the scan for to be able to project patterns on. So, but then that limits us at this stage. It limits us to radially symmetrical shapes. So like that's definitely a limitation of the system. And like ideally in next iteration, we'd like to find solution to like complexify the shape, and maybe scanning would be an interesting avenue.
Because you have like a wheel that is going around them, so you kind of feel like it would be just like a slick scan of the whole thing as it rotates.
Well, our scanner is kind of that actually. Yeah. And the thing with clay is like even if I mean maybe it's also because we're not expert, but even if you do everything on like a symmetrical platform, when it dries, it might dry with deformation. So it's not like, and it often does, like for different reasons, but one of them is like one of the surface is flat on something that has friction, while the rest of the object is in like just in contact with air. So the base and the top of the object might dry at different rates, and the shrinkage might be slightly different. So yeah, so that's, and we went to the just like good old physical measuring way to kind of, but then implemented a way to make that system like easily iterative. Yeah, that's kind of the strategy we went for, but which was successful to a certain degree, but there could be other ways, I think, to do that.